This is my third lecture on sensitivity analysis using the graphical method. In the first lecture, we graphically obtained an optimal point of profit maximization problem, and we found that point B is the optimal point with x1 equal 24 and x2 equal to 8 and a profit equal to $1,360. In the lecture 2, we discussed about the sensitivity analysis, and we discussed that there are two questions that needs to be answered. The first question is, how will a change in the coefficient of the objective function is going to affect the optimal solution? And the second question, which is important for sensitivity analysis, is that how the change in the right hand side value of a constraint affect the optimal solution. So question number one was discussed and answered in lecture part 2. In this lecture, we will see how the change in the right hand side of the constraint will affect the optimal solution. So just a brief recap of the concepts. In the first part, we discussed the graphical method. In the part 2, we looked at some important concepts like how the slopes are calculated and what are the slopes and the effect of coefficients of x1 and x2 on slopes, how the line becomes steeper and flatter. And then we also discussed that multiple optimal solutions will exist if the slope of the objective function will become equal to the slope of the constraint, or simply put, if the line objective function line it becomes parallel to the line of the constraint, then we will have multiple optimal solutions. In this lecture, we will look at the effect of changes in right hand side on a line. We will look at slack variables, and we will look at the binding and non-binding constraints. So let's start lecture number 3. So let's see what happens if we change the right hand side of an equation. Here there is an equation shown on the screen: 40x1 plus 50x2 equal to 1200. This equation of a line can be plotted, and it is plotted in the blue color as shown on your screen. Now we want to know what happens if we change the right hand side of this equation, that is 1200. So let's see, in our first case we increase the right hand side. We increase it from 1200 to 1600, and we plot it by first putting x1 equal to 0 and finding x2 equal to 32. This procedure has been discussed repeatedly in lecture number 1 and 2, so I think by now you must be very much familiar how it is being done. So in a similar fashion, we will put x2 equal to 0. We will find x1 equal to 40. We have now obtained 2 points. Using these 2 points, this increased right hand side equation can be plotted, and it is plotted in the green color here. Now let's see what happens when we decrease the right hand side. So now from 1200, now we have decreased the right hand side to 800, and now we are trying to plot it using the similar procedure. When x1 is equal to 0, x2 equal to 16, and then we will put x2 equal to 0 and find x1 equal to 20. This will give us 2 points. We can, using these 2 points, we can plot it, and it is shown in the red color on the screen. So if you closely observe these three lines, this red, blue and the green, you will see that these lines are parallel, meaning that the slope of the lines does not the slopes of these lines are same. That means the slope does not change when the right hand side changes, either it increases or decreases. The only difference is that when we increase the right hand side, the line moves away from the origin, or moves away, as you can see the green line here, it has moved away from the origin. And when the right hand side is decreased, the line moves towards the origin. Now, having understood this, let's move to the second point, and that is the concept of the slack variables. Slack variables are basically unused resources. So in a maximization problem, we define slack variables for each constraints, and we denote them with SI. S is for slack, and I represents the number of the constraint we have. So let's say in our problem, the first constraint was a labor constraint. So we will change our labor constraint x1 plus 2x2 less than equal to 40, and we will introduce a slack constraint here. So when we introduce a slack constraint, this inequality turns into equality. So that means that by the introduction of the slack constraint, the weak inequality has now changed into a equality. In a similar fashion, we can write for the clay constraint that was 4x1 plus 3x2 less than equal to 120. We will introduce the slack constraint here. Now you can see that in the first labor constraint it was s1, now this is s2. So basically 1 is for the first constraint, 2 is for the second constraint. Basically we have the general term I here, so it is just the number of the constraints. If we have 3 constraints, then we will also introduce s3. Now these slack constraints, they do not add anything to the objective function, so but we still add them in the objective function, but they contribute nothing. So to make sure that they contribute nothing, we will rewrite the objective function as 40x1 plus 50x2 plus 0s1 plus 0s2. So we s1 and s2 are multiplied by 0, ensuring that they contribute nothing to our objective function. So summarizing this, we can write the complete model as our objective function and the constraints. And the third constraint, that is the non-negativity constraint. A model written like this, it is said to be written in its standard form. So this is a standard form, this of writing a mathematical model. Now, once we understand the concept of slack variables, let's find the slack variables at the different points. So in our problem that we discussed in lecture number 1 and lecture number 2, we have 3 points A, B, C. Although we are more concerned about point B, but let's, for the sake of demonstrating that how are the slack variables are calculated, I will calculate slack at point A, at point B, and point C. So first calculate the slack at point A, whose coordinates are 0, 20. So the labor constraint is x1 plus 2x2 plus s1 is equal to 40. Here, using the coordinates of A, x1 is 0 and the x2 is 20 plus s1 is equal to 40. That means 40 plus s1 is equal to 40, meaning s1 is equal to 0. This was for labor. Now write it, calculate it for clay. That is 4 into x1. X1 is at A is 0 plus 3, x2 is 3 into 20 plus s2 is equal to 120, and if I solve it, this will give me s2 is equal to 60 pounds. So what does that mean? That means at point A 0 hours of labor are unused, whereas at point A 60 pounds of clay is unused. Now I'll do it for B. I will do it for B, and at B the coordinates are 24, 8. So for labor it will be x1 24 plus 2 x2 2 into 8 plus s1 is equal to 40. That means these two, as these two numbers they sum up to 40, this means s1 is equal to 0 here. For clay we have 4x1 4 into 24 plus 3 into 8 plus s2 equal to 120. Now as these numbers sum up to 120, so this also implies that s2 is equal to 0. So this means at point B, which is our point of concern, s1 is equal to 0 and s2 is equal to 0. At point A, s1 is equal to 0 and s2 is equal to 60 pounds. So you can calculate it for C. I'm just writing it directly. At point C, the labor will be, for the labor s1 will be, x1 is basically 30 and x2 is 0. S1 will be 10 hours and s2 is, I think it should be 4 into 30. s2 will be 0. So this is for the s1 and s2 at point C. Now based on these values of slack variables, we define the binding constraint. So a constraint that has 0 slack at the optimal point, it is a binding constraint. So these binding constraints, they are very important for the sensitivity analysis of the right hand sides of the constraints, because a change in the right hand side of a binding constraint, it will have an impact on the objective function. Why? Because in the, as we discussed, that in the binding, if a constraint is binding, that means there is no slack in it. So if we change a the right hand side of that constraint, means that we, let's say we add more resource to it, or we reduce the resource to it. So in our case, let's say if we increase the labor hours or the clay, that so this increment in labor hours or clay will have a direct bearing on the objective function value, and a change in the right hand side of the non-binding constraint, it has no impact on the objective function value. So this is important thing, and we will use this concept while doing the sensitivity range of the right hand side of the constraints. So with these things, with these three things, now let's discuss how the sensitivity range of the right hand side of the constraint is done. First, a formal definition that tells us that the sensitivity range of the right hand side, it is a range over which it can change without altering the mix of decision variables in the solution, including the slack variables. Sounds tricky, but don't worry, we will break it down, and let's say, and we will refer to our original problem. And the problem was, in that problem we had the optimal point at B. So at point B we had the decision variables x1 is equal to 24 and x2 is equal to 8, and we had the slack variable that we just calculated, s1 equal to 0, s2 equal to 0. So now, this definition is telling us that if we make a change in the right hand side of the constraint, then then the quantities of x1, there was some quantity of x1 that is 24, x2 equal to 8 in our optimal solution. So when we make a change in the right hand side, then after making this change, we must still produce some quantities of x1 and x2, although their values will be different because now we'll be having a different values of resources like labor and clay, but there must be some values of x1 and x2 in it. So that means solution mix should be the same. The same decision variables should exist in the should say the same decision variables should exist when the right hand side of the constraint is changed. Similarly, because we saw in our previous slide that point B was optimal point, and the point B was found by the intersection of the clay and the labor constraint. So these two constraints were the main constraints that helped us identify the feasible region, and these two constraints were used to identify the optimal point. Now when we change the right hand side of the constraint, so no new constraint should take precedence in it. That is, the when we are changing the right hand side of the constraint, the original optimal solution, the constraint used to find the original optimal solution should be again, should also play the same role in the new solution. So that means no new limitation should take over. Finally, the definition said something about including the slack variables. That means, let's say if in the original optimal solution slack was 0, now we change the right hand side, then again we should be mindful that after changing the right hand side of the constraint, slack should again be 0. It should not be some value. And if, let's say, if we had a solution at point A, because in our previous, in the previous slide I showed you that slack at point A, there was some value of slack s2 equal to 60. So let's assume that if we had point A as the optimal point. Now when we increase the right hand side of the constraint, then that's the non-binding constraint should remain non-binding. That means that it should not suddenly become fully used or become binding. So this situation, in a nutshell, the solution structure should remain the same. In graphical method, we basically find the transition point where this solution structure changes. We find those points between those 2 points, this solution structure, the requirement of the solution structure that we just discussed here, the requirement of the decision variables and slack variables, it should remain same. And how it is done? So to analyze the sensitivity range, we replace the right hand side of the constraint with the letter Q and the subscript I. I again, as we used with the slack SI, I is for the first constraint, second constraint, and so on and so forth. So the variable qi, it can have a maximum and a minimum value, and within that maximum and minimum value the solution will remain unchanged. So we have the labor constraint x1 plus 2x2 less than equal to 40. We will replace the 40 with x1 plus 2x2 equal to q1. Q is the sensitivity range of the constraint, and this q1 will have a maximum value and a minimum value. By that I mean that originally we had 40. We want to see how much we can increase the value of the labor hours, and still the solution structure remain same, that is x1 and x2, and the slack, they should be they should exhibit the same characteristics. And similarly we can also reduce the value of the 40 and see how this solution structure still holds. So this q1 has two values, q1 max and q1 min, and we want to say that as long as the q1 stays within this range, the solution structure remains unchanged. Similar thing holds for the clay constraint. For x1 plus 3x2, we will replace 120 with the q2, and q2 has the two values, q2 max, q2 min, and these values define the sensitivity range, and meaning that as long as q2 stays between these two ranges, this range, the solution structure remains unchanged. Now let's find out how, let's see how it is actually done. So let's say, let's in the first phase we want to find the sensitivity range of the labor constraint. This is our labor constraint. Originally we were given the 40 hours. We want to see how much can we increase the number of hours and we still end up with the same solution structure. So again, keeping in mind the definition, the first definition was that you have to see the optimal point. So point B is the optimal point, and we discussed that no new limitation should enter when we increase the right hand side. So point B in the original solution was found by clay and labor, so it should, these two constraints should stay important in our analysis when the right hand side of the constraint is changed. So and the both constraints are binding, that means slack is 0, so that's another requirement. So when we change the right hand side, they should remain binding. So first we find the maximum value of the labor hours. So q1, we described it as q1 and q1 max, basically the maximum value of the labor hours that can give us the same solution structure. For that we will keep the clay constraint at its position and we will increase the labor hours. And we discussed in our initial in the first three third slide, in the first in the first 2 3 slides, that when we increase the right hand side of the constraint, the line moves away from the origin. So that means we will hold the, this is the clay line by the way, and this is the labor line. So we will hold this clay line at its position and we will move the labor line away from the origin. Why move away from the origin? Because we are increasing the right hand side of the labor constraint. So we want to find the maximum position of this point B. Point B is basically intersection of these two constraints. So as we move the labor line away from the origin, we want to see where, what is the maximum point, what is the position of the maximum position of this point B where these two where these two constraints still intersect. So let's see how it's done. So you see in this slide I have kept the clay constraint at its position and I have moved the labor constraint up. So as I moved it up, the feasible region has changed. I just go back to the previous slide to just help you visualize. This was my original feasible region. When I moved the labor constraint, now the feasible region has changed. And if I move it further away from the origin, I will end up at this point. Now this is the point B, which is the maximum point where these two lines can intersect. Now, just for the sake of the information, B 0 comma 40, we found these all these points, we found these points in our lecture 1. So we see that at B 0 comma 40, these two lines intersect, and this is the maximum point where these two lines can intersect. So at this point, let's find the maximum value of the labor hours. We will write it as x1 plus 2x2 equal to q1 max. Now at B, where coordinates are 0 comma 40, we will put x1 as 0 to x2 as 40. So q1 max is equal to 80. That means that we can increase the right hand side of the labor hours from 40 to 80, and we will still end up with the still end up with the same solution structure. Now let's find the minimum labor hours. Now the procedure is same, just to reiterate and keep, so that you should remember this thing, that we want to find the minimum labor hours. We want to keep the clay constraint at its position, similar like we did before in the first phase. We were moving away it moving the labor line away, because this we were increasing the value of the 40 to 40, 50, 60. Now when we decrease the value of the 40, this line will move towards the origin. Now we will keep the clay constraint at its position. We will move the labor constraint. We want to find the minimum position of B where these constraints can intersect. So just for this, if you see for the visualization, as I move this labor line towards the origin, I have found a new point of intersection of B, and I can see that there, if I move it further towards the origin, then this is the point, this is the lowest point where these two lines can intersect. Again, the coordinates of B30 we found it in the first lecture. So now at this is the lowest point 30 comma 0, where this is the lowest position of the B where these two constraints can still intersect. So I'll find the minimum value of labor hours x1 plus 2x2, it is equal to q1 min. This is happening at B30 comma 0. So 30 x1 is equal to 30 plus 2 into 0 is equal to q1 min. That means q1 min is 30. So to sum up, this means that q1 can be varied from 30 to 80 hours, and we will still have the same solution structure. So this is the sensitivity range of the labor constraint. Now we'll find the for the sensitivity range of the clay constraint. This is our clay constraint, 4x1 plus 3x2 less than equal to 120. The procedure is same, just I'm repeating it again. Point B is the optimal. Point B is found by the intersection of the clay and labor. So is this, when we increase the right hand side of the clay constraint, again the optimal point should be found between the labor and the clay constraint. Both constraints are binding, that is slack is 0. For finding the maximum value of the clay, that is Q2 max, we will now keep the labor constraint at its position, and now we will move the labor constraint. Right now we are finding the maximum value, that means we are increasing the right hand side, so this clay constraint can move away from the origin. So we find the maximum position of B where these constraints can intersect, and as I mentioned earlier, when I will move this line away, clay constraint away from the origin, this visible region will change, as you can see here. So this you see that this is a different visible region. Now if I move this line further away from the origin, I will end up at this point, and this point B is the maximum point, and it is still in the visible region. This is a very important requirement, and now this still ends up in the visible region. So I can find here that the maximum range of the clay, q2 max, and this is happening at B 40 comma 0. Put 4 x1 is 40 plus 3 into 0 is equal to q2 max. That means q2 max is equal to 160 pounds. So this is the maximum value of the clay that we can use, and we will still end up with the same solution structure. Now let's find the minimum value of the q2. For finding the minimum value of q2, again repeating the procedure, labor hours will be kept, labor hours line will be kept at its position. We will move the clay constraint now, because we are finding the minimum value, meaning that we are now decreasing the value of 120 to a lower value. That means this line will start moving towards the origin. We find the minimum position of B where these constraints can intersect. So now if you just visualize it, that here when I move this green line towards the origin, the feasible region is now changed, and I find this point. Now if I further push it towards the origin, then this is the lowest point where these two coordinates can intersect. So I will find the q2 min by 4x1 plus 3x2 is equal to q2 min, and this is happening at b 0 comma 20. Putting the values, 4 into 0 plus 3 into 20 is equal to q2 min. That means q2 min has a value of the 60 pounds. So that means I can vary q2 between 60 and 160 pounds, and I'll still have the same solution structure. So this is the graphical method of finding the sensitivity range of the constraint. So summarizing the results, uh, in the very first video we found this point B through graphical method. This was our lecture 1. In lecture 2 we found the range of coefficients of x1 graphically, and the range of coefficients of x2. This was done in lecture 2. And right now we have found that what is the sensitivity range of the labor constraint and what is the sensitivity range of the clay constraint. So after finding these values, in the next lecture we will look at the shadow price, the reduced cost, and we will verify our results on Excel. Thank you.